right, so we're going to start up 4.2 today. And pretty much what we're looking at is probably takes about 3 days to get through this section. We'll spend Thursday doing some review and then probably quiz by Friday. Should make the most sense here. Just quiz over 4.1, 4.2. So learning target here is going to be pretty straightforward, but it's going to be I can graph rational functions. And we've done a little bit of this already. You know, we graphed the real basic reciprocal function back in 4.1. But now we're going to look at these being a little more complicated at times. I don't want to do this question, though. I think it's not really necessary. So let's go ahead and jump right down to this example 1. So it says, rewrite g of x, which is this function right here, using long division. Okay, we'll do that in a sec. How is the quotient related to the reciprocal function 1 over x? Sketch the graph. All right, so this just says basically do this as a long division problem. So, remember long division from last chapter. We're going to take 4x, and from it, we're going to divide x minus 3. All right, so when we do that, remember long division, you look at the lead terms and you say, okay, this one would have to get multiplied by 4. So we put a 4 here. And then we multiply 4 times x and 4 times the minus 3. And we subtract that from what's above. So in this case, the 4x's cancel, and then we have nothing minus a negative 12, which is a positive 12. And that ends up being our remainder. So this is like a one-step long division, which is actually nice. It's pretty easy to do. And remember how you write the remainder as plus 12 over the divisor. And so that would be our long division answer. Now, what's actually pretty cool about this is it says, how's the quotient related to the reciprocal function? How is this related to this? Well, now, if we take a look at it, we're seeing, well, we have a number over an x with the minus 3 on it, and then we have a plus 4 to it. And if you remember the transformation stuff from the end of 4.1, this actually all fits as to what's going on. This is going to show us, and this is, let's jump right to here before we sketch the graph. This says rewrite it in this form. So, where you put this part and then you put the plus 4 after it to show like the all the transformations. The cool little move here is we can now just look at this and we know everything that's going to be happening here because we know how transformations work, right? So we can look at this, we can say, okay, that's going to stretch it by 12. We know this is going to make it go right 3. And we know this is going to make it go up 4. And so based off that, we can make this graph by hand, and then we'll check it with the calculator just to kind of show things. So instead of having our asymptotes at 0 and 0 here, it's going to be shifted right 3, 1, 2, 3, and up 4, 1, 2, 3, 4. And so our asymptotes are going to run right through this spot. And normally, it's in these 2 quadrants here. The only difference is it's going to be stretched by 12, so it's going to be wider than your typical graph. So, it's going to be something kind of like this is what we'd be looking at. So we can actually make that sketch by using long division to rewrite this. If we had to try to graph this problem, this would be a lot harder to do. But we use long division as a way to get in a form that we're familiar with. Now, just to show you that this does, in fact, match up and it is the same thing, let me throw it in my calculator real quick and we can compare those. So, all right. So there's the original problem typed in, and it should look like this. Let's take a look. And I'd say it's looking pretty good. Now, the one thing that you're going to run into with the calculator, you cannot just live for the calculator, the graphing, whatever, because it's not going to be super obvious exactly where this is at. Like, it's hard to tell if this line is at, 3 or 4 or 5. It's not necessarily really easy. It is at 3. And, this one here is at 4. But it is hard to tell in the graph. There's not a great way to get it from here or even on decimals or anything. So you do have to be able to do this to identify these. So from this, we can say a couple things. We can say this has a vertical asymptote at x equals 3. We could say it has a horizontal asymptote at y equals 4, which are what we got from the problem kind of working out and doing everything. So that's the first kind of main idea today is that right there, using long division to write it into this kind of transformation form that we're used to and being able to analyze it from there. So on this page, we don't need to do both these, but let's go ahead and just do one of them. So go ahead and try A on your own here. See if you can do the long division, get it in the form, and show what the graph's going to look like. All right, so I went ahead and I did the long division part of it. I took my 6x, I divided by the 2x plus 1, and I got this. And I rewrote it so it was kind of in the form we're used to. And I can see a couple things. I see that this does shift it up 3. This one's going to be reflected. Remember we talked about that back on Friday. It's also going to be stretched by 3. But the one thing we run into here is there's this plus 1, but there's also a 2 here. And so we actually have to think of this as what would our 0 be here? Like what number is going to make this equal 0? You probably remember this back from chapters 2 and 3 is to make this equal 0, that would actually be a negative 1/2. If you did negative 1/2 times 2, it'd be negative 1. Plus 1 would give you 0. The shortcut for that is it's always the opposite of this number divided by that. But we can actually figure out that negative 1/2 is going to be where that vertical asymptote is going to be, where it's shifted to. So a little bit trickier here in this case. So let's just kind of talk about where this is going to be and what it's going to look like. So it is going to be shifted left. So it's x equals negative 1/2. So it's going to be here. And then the up 3 means that that horizontal asymptote is going to be shifted a little bit there. So we're going to get this style of graph. And then as far as where is it going to be, it is reflected. So instead of being in these two quadrants, it's going to be in these two. So sorry, I'm kind of overlapping my problem here. But we're going to get a graph that looks a little something like that. And with all these, we can check them by graphing, which is smart. And so I throw this in my graphing calculator, and I see this, which, aligns, matches up with what I just did there. But please trust me when I'm telling you this is if you just rely on this, you're going to get these wrong. And the reason I say that is you're not going to be able to really tell exactly where these asymptotes are. Like if I asked you where this line was, it's really hard for you to know if it's at -1 or 0 or -0.5 or -0.4 or anything in there. So you got to be able to do the pieces to figure out, okay, here's where my asymptotes actually are located. Because one of the big things you're going to see going forward is you got to be able to say, where is the vertical asymptote? Where is the horizontal asymptote? So vertical asymptote, this one is the one that goes through -1/2. So x equals -1/2. Horizontal asymptote is the one that went through 3. Y equals 3. Now, the good news is normally this long division method really isn't the most efficient way to do these. So kind of the next step is what we're going to do in example 2 here is really what I would call the better way to do this style of problem. So this sort of shows you a way to think about it, but I personally don't do many problems like this. Here's kind of the way you want to think of these. So first off, rational expression, just to give you a really clear definition, is anytime you have a ratio of two polynomials. So you got some polynomial divided by some polynomial. That's it. That's what a rational function is. And like we've talked about, we can't get a 0 down here. If we get a 0 down here, it's undefined value, and so we have to restrict those values from our domains. And those are also what cause the asymptotes to be where they are. So let's jump right to this example 2. So this one says, what are the vertical and horizontal asymptotes of this rational function? So here's the thought process on this. If you want to find the vertical asymptotes, those are when at whatever x values where it's undefined. In other words, they're the zeros of this denominator. It's whatever makes this denominator be 0. So your best route to do this is basically just factor the denominator in order to see where its zeros are. So if I took this function and I just factored it, so I don't have to do anything to the numerator, it's fine as it is. But if I factor this denominator, factors of 12 that add to 7 would be 4 and 3. And I can factor it to x plus 4 and x plus 3. What that lets me do is I can look at that and I can say, okay, there's some numbers that x can't be, because if x is -4, I get a 0 here. And if x is -3, I get a 0 here. So those zeros are exactly where the asymptotes are going to be. So when this question is asking where are the vertical asymptotes, which again, I always just abbreviate VA, those are going to be the two of them. And so I mentioned the other day real briefly that you can have more than one asymptote. And just to show you graphically what this one looks like is when I put this one, I put it just when my y equals, put the two quantities in parentheses, divide the two. But when I graph it, I do see that two asymptotes make sense here. There's actually one here and here. And if I go up a little higher, there's a part of this graph that kind of exists really narrowly in here. But again, the fact that at -4 and at -3, there's two spots this approaches. This is, again, why you got to understand the concept, because you might just look at this graph and think it just had one asymptote, but that's not the case. So you really got to understand that, all right, the zeros of my denominator are where my vertical asymptotes are. So that's exactly what this says right here, this little part kind of on the bottom. So that's the first part of this. I'm halfway done. I've found the vertical asymptotes. Now the horizontal asymptotes have a couple little rules. So on the next page, there are 3 cases. And these actually aren't too bad. So what these cases are is, depending on, you're going to compare the degrees in your numerator and your denominator. So degree, remember, the highest power. So like in this case, this one has a higher degree in the bottom. So when the higher degree is in the bottom, then the graph always has an asymptote at y equals 0 every single time. So bigger degree in the bottom, then y equals 0 is your horizontal asymptote. If your bigger degree is on top, this is case 2, then the problem has no horizontal asymptotes. Okay? And then the third rule is if the two have matching degrees, these are both second degree, then all you have to do is divide the coefficients. So in this case, 2 divided by 1. If we divide the lead coefficients, then that's where that asymptote is going to be. 2 divided by 1 is just 2. So we say horizontal asymptote at y equals 2. So those are our 3 cases. Again, just to recap them real quick. Bigger degree on the bottom, y equals 0 is your asymptote. Bigger degree on top, no asymptote. Same degree, divide the coefficients, and whatever that number is the y equals, that's where your horizontal asymptote is. So for our specific problem, we had, this is the one from the previous page there, we had lower degree on the bottom. So this one has a horizontal asymptote at y equals 0, which actually also makes total sense. The graph that I had in here, this thing is bottoming out right at 0. Everything fits there. This makes sense as far as what it's saying. So those are your 3 cases. So let's look at a couple other examples here. All right, so here's one. Same question. What are the vertical or the horizontal asymptotes? Vertical asymptotes come from factoring the denominator. So as I go to figure these out, let's factor this denominator. So it would be, looks like -4, +2. So x minus 4, x plus 2. Awesome. So that means I'm going to have a vertical asymptote at 4 and at -2. Okay, don't make that harder than what it is. This is using the skills we've been doing for months now. If you can factor and identify the zeros of the denominator are where the vertical asymptotes are going to be. And then for your horizontal asymptote, follow the 3 cases. In this case, degrees are equal. And when the degrees are equal, divide the leading coefficient. So 2 over 1 is 2. So same numbers as the previous one. So it's just going to be y equals 2. And like we talked about a couple previous days, vertical asymptotes, ones that go up and down, are always x equals. Horizontal asymptotes, running left and right, are y equals. So we can graph this one and do a little visual check too. Okay, so I throw the equation in my calculator. Again, just the original problem. Make sure you use parentheses if you're typing it in. And when you graph these, a lot of times they're going to look pretty wild. So like the graph of this one looks like this, which is probably unlike anything you've really ever seen before. But what we can do is we can look and see, do the things that I said make sense? X equals 4. Vertical line, yeah, that does make sense. It's approaching but not touching right there. Vertical line at -2. Yeah, perfect. That's exactly what this is saying is going on. And then horizontal asymptote at 2. Does this graph bottom out towards 2? Yeah, absolutely. So right here, this is heading towards 2. This is heading towards 2. So these 3 values I came up with all fit with exactly what I see on the graph. But you got to kind of be able to do this to check it with the graph. If you just have this, I doubt you're going to be able to identify these as easily. So you kind of want to make sure you can do this and then use the graph to check things out. Okay, go ahead and try this one out, and I'll do it as well. Okie dokie. So I went ahead and I factored my denominator because I know zeros in my denominator are where I get my vertical asymptotes. So pulled out GCF of 3, left with a difference of squares. So that's just x plus 2 and x minus 2. So therefore, the zeros would be -2 and 2. So x equals -2, x equals 2. Those are going to be where my 2 vertical asymptotes are. And then horizontal asymptote, that's your 3 cases. So that previous page, once again, we had equal degrees. So we're going to do coefficient divided by coefficient, 1 divided by 3. So 1/3. So y equals 1/3 is where we end up at in this case. Okay, and you may not feel 100% on this, which is okay. This is day 1 of 3. Like we're going to be working the same exact skill for a couple days. So you just want to start getting a feel for it by Wednesday, Thursday, if you feel like you're kind of lost, then worry about it. But right now, this is day 1 of this, what is kind of a weird new thing. So try it out and we'll keep working.